In this video, we're going to be exploring section 10.2, which is all about polygons. And we're going to be examining mostly their angles, the angles of polygons. We'll spend a little bit of time talking about triangles, the idea of congruence. We'll discuss what a regular polygon is and how to draw them. So first of all, let's throw up the picture of just a random polygon. And remember, a polygon has to have some straight sides and they can't cross. Um, and as we look at this, you're going to see that it's got 1, 2, 3, 4, 5, 6 different sides. So this is a hexagon. Now, at each vertex, there is an angle here, 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 and the red one there, right? So there's 6 different angles. And every vertex is going to be between 0 and 360 degrees. It'll be more than 0. It'll be less than 360 degrees. In this drawing, that one is less than 20 degrees. Angle B is less than 20 degrees. And angle D, this is actually and so is angle A. Both of those are greater than 180 degrees. These are both reflex angles. They're more than 180 degrees. But again, when you're drawing a hexagon like this, as one gets bigger, another one might have to get a little bit smaller. So there's always a relationship in any polygon between the number of sides it has and the number of, or the sum of its angles. Let me make this so you can see this. Sorry. There's a relationship between the sum of all the angles in the polygon and its number of sides. Now, the one we may be most familiar with is a triangle. And in any triangle, there's 3 angles in a triangle, and they're always going to add to 180 degrees. And we're going to do a little experiment to demonstrate this. And so what I want you to do is, if you can grab any sheet of paper and just cut a triangle, it doesn't matter what the triangle looks like, just cut a triangle out of any sheet of paper. I have cut out my little sheet of paper here. And now what we're going to do is we're going to take our triangle and we're just going to rip off each corner, so each vertex, right? So I'm going to rip that off. I'm going to come back to my paper. I'm going to rip this one off. And I'm going to do the same thing with this one. So I'm just tearing the corners off those. And now what we're going to do is we're going to take the vertices of our triangle and we're going to piece them together. What do you notice? It makes a perfect straight edge right there, right? And it doesn't matter what your triangle looked like to start, it'll always look like that. So those 3 angles that we had, right? Here was one of the angles in our triangle. Here was one of the angles. And here was one of the angles. If you combine them, put them all together, they're always going to add up to 180 degrees. You can see a similar example of what we just demonstrated here with this more technical drawing. Now, we are going to analyze this a little bit more because in geometry, we often like to prove things. And so what you're going to see in this next diagram is, first of all, a pair of parallel lines. So line L passes through point A, and it's parallel to line BC. So we have 2 parallel lines. And then we'll note that we have this triangle, ABC. And the first question for you is, why is the measure of angle 2, which is this one right here, why is that equal to the measure of angle 2 prime? That little apostrophe looking thing is called a prime, 2 prime. So why is this angle equal to this angle? And take a moment to see if you can answer that question. You may have noticed even that there's another question here question B, which says, why is the measure of angle 3 equal to the measure of angle 3 prime? Well, that's this one and this one. And the answer to both those questions is the same. Those are alternate interior angles. We discussed that in the previous video. There is a set of parallel lines. There is a transversal running through them, and opposite interior angles, these and these, are always going to be equal. We just happen to have a second transversal running that way, meaning those two are equal. So that's why angle 2 and 2 are equal, 2 and 2 prime, and angle 3 and 3 prime are equal. So the next question for you to analyze is, how does this fact show that the sum of the measures of angles in triangle ABC is equal to 180 degrees? So we have angle 1, 2, and 3. How can we use that fact to prove that it's equal to 180 degrees? Take a moment and see if you can stare at that and figure that out. So one of the things you might have noticed is that if we look at this angle here, the angle that includes 1, 2 prime, and 3 prime. So the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3, but 2 and 3, it's prime. 2 prime and 3 prime, right? So this, and this, because all those make a flat line, that is 180 degrees. We know that much, okay? We know that much. But we also know that angle 2 is equal to angle 2 prime. So we can substitute angle 2 in for angle 2 prime in this equation. Same thing with angle 3. It's equal to angle 3 prime. So we can substitute the measure of angle 3 in for the measure of angle 3 prime. And measure of angle 1, that still stays the same. And now we can see that angle 1 plus angle 2 plus angle 3 is equal to 180 degrees. And so we use this fact of these alternate interior angles being equal to say, well, whatever this and this are, they're the same down there. And so if these added up to 180, these also have to add up to 180 degrees. That's one example of what a geometric proof looks like. So let's start now examining the angles of polygons. That was the angles of triangles. Triangles make 180 degrees, and we're going to use that fact as we explore the angles of different types of polygons. And so I'm going to start with this picture right here, because the trick, it's a little geometric trick that we do. The sum of the angles in a polygon that has 4 or more sides can be found by subdividing the polygon into triangles, so that all the vertices of the triangles are the vertices of the polygon. So what does that look like? I'm just going to make a randomly drawn 4-sided figure. Let's get a nice, so there's a side, and there's a side, and there's a side, and there's a side. All right. So what this means is when we subdivide the polygon into triangles, we are going to pick one diagonal and just going to draw a little dotted line across that diagonal. And what we've done is we've subdivided this into this triangle here and this triangle here. And I'll give you a neater version of that. It looks like this. So here's that same sort of idea, okay? And what we'll notice is that we've got, again, triangle and triangle. Now let's think about what we just learned about the angles of triangles. Let's look at this green one over here. Well, we know that angle 1, I'll just use a 1 instead of the whole angle symbol. 1 plus 2 plus 3, all of those angles have to add up to 180 degrees. And Angle 4 plus angle 5 plus angle 6, all those measures also have to be 180 degrees because they both are triangles. Well, if we add 1 plus 2 plus 3 to 4 plus 5 plus 6, that gives us this angle, this angle, this angle, and this angle. It gives all of them. And so that's going to be 180 plus 180, which is equal to 360. And that will be the case no matter what our quadrilateral looks like, if it has four sides. Even if it's a even if it's something convex like this, that still works because we can just cut that into two triangles there. They both have 180 degrees, and so this would have 360 degrees. So we know every quadrilateral is going to have 2 times 180 or 360 degrees. The key is that knowing a triangle has 180, so how many triangles can we make? So if it has 4 sides, it's going to be 2 times 180 to be 360. Let's look at another situation. Let's look at this. Let's look at a pentagon. So I'm going to stick a picture of a pentagon down here. A weird looking pentagon, not what we normally think of as a pentagon, but it has 1, 2, 3, 4, 5 sides. And so we can cut it up into 3 different triangles. If we use this as our starting vertex, line, line, we now have 3 triangles. Each of those triangles has 180 degrees. So if we add all of those sides to all of, or angles to all of these angles, to all of these angles, we're going to get 180 plus 180 plus 180, or 3 times 180. So if it has 5 sides, it's 3 times 180, which is 540 degrees. So every single pentagon, if you measure all 5 of its angles and add them together, it will always equal 540 degrees. Let's do one more. How about an octagon? So I'm just going to say that. Make sure you remember what an octagon is. So take a moment, see if you can sketch an octagon, subdivide it to have triangles only, and figure out what is the total angle measure of all of an octagon's angles. Once you sketch it, it's going to look something like this. So you make your octagon, and then count how many triangles you're able to subdivide from it. 1, 2, 3, 4, 5, and 6. Each triangle has 180 degrees. So in our octagon, which has 8 sides, it was 6 triangles times 180 degrees each, which is 1,080 total degrees in our octagon. So maybe you're starting to notice a pattern here, a relationship between the number of sides that our polygon has and the number of triangles it can be subdivided into, and thus the number of total degrees it has. So what we're going to do is start to generalize this. Maybe you can already do it. So here is a little chart. We've already done our triangle, our quadrilateral. We've done our pentagon, which was 540. We've done our octagon, which is 1,080. See if you could fill those in. Also do 20, and then see if you can answer this question. How many degrees would be in any n-sided polygon? N, again, means any number of. Take a moment and see if you can do those. I'm going to pull up my calculator here, and we're going to do a little multiplication. So rather than drawing them, maybe what you started to notice in our little chart we laid out was that the number of sides in our polygon, if we subtract 2, that's how many triangles we can get. So if we had a 6-sided figure, we could do 4, take away 4, or take away 2, we get 4. 4 times 180 is equal to 720 degrees. If it has 7 figures, it's 5 times 180 to be 900 degrees. If it's 20 sides, we'll take 18 times 180 to get 3,240, 30 to 40 degrees. So what would we say for n? Let's generalize this algebraically. For any, try this again. Here we go. For any polygon of n sides, the way we would calculate its total angle measure would be 180 times n minus 2. Subtract the number of sides, multiply that by, subtract the number of sides minus 2, multiply that by 180. So now we're going to move on to another topic, the idea of what we call congruence. Congruence. Congruence is pretty simple. It basically means that two things are the same. If we talk about two-dimensional figures like we're doing now, plane figures, then we say that two plane figures, such as these, not those, are congruent if one can be placed on the other so that they coincide. Imagine taking this yellow one, flipping it over, rotating it, reflecting it, and it would lay right over top of that orange figure exactly. Another way to say it is they just have the same shape and size. Things that are congruent are the same. We can have congruent line segments. Congruent line segments have the same length. Congruent angles have the same measure. So that's going to be an important concept moving forward as well. So let's extend this to the conversation of polygons, specifically something we call regular polygons. So a polygon is a regular polygon if it satisfies two conditions. One is that all the angles are congruent, and 2 is that all the sides are, the sides are congruent. So regular polygons have angles that are congruent and sides that are congruent. Here is what a few of them would look like. We discussed an equilateral triangle before. That is called a regular polygon. A square is a regular polygon because all sides and angles are the same. This is what a regular pentagon would look like, a regular hexagon, and a regular heptagon. Now, sometimes it can be helpful when you're learning something to see what's not the thing you're trying to define. And so here are two examples of polygons that are not regular polygons. In the first one, why is this not a regular polygon? A rhombus has equal side lengths, but if you recall, the angles are not equal. The opposite angles are equal, but the adjacent angles are not. This angle and this angle are not equal, so that is not a regular polygon. This is a hexagon, and when I look at that, I see that we've got some equal sides, and actually all the angles are congruent here. All of those angles are the same measure, but this side and this side are not equal to all the others, so those are not regular. So let's conclude this with a conversation about how we draw regular polygons, how we can draw them. And it's going to involve an investigation of their angles. So we have three special angles in a regular polygon, and they are the vertex angle, the central angle, and the exterior angle. So let's examine these. The vertex angle is what's formed between two adjacent sides of the polygon. So where your polygon's sides meet up, that's going to be a vertex angle. If we can take our polygon and go to the very center point, that's a very useful point a lot of times. And if you draw then lines to adjacent vertices, the angle that's between those two lines would be called the central angle. And then finally, if we take our side here and imagine extending one of the sides like that. Imagine extending one of the sides, and we look at the angle between the adjacent side and that extension. That's going to be the exterior angle. Now you might notice that the vertex angle and the exterior angle are what? What property do they have? They would be supplementary because they'd add up to 180 degrees. So a vertex angle and an exterior angle are supplementary angles. So let's investigate a regular pentagon. So here is a regular pentagon. And what you'll also see are these other lines that were drawn from that point, the diagonal. Why do we do that? To turn it into three different triangles. And so what we're going to try to calculate here is how big are the angles in our regular polygon. And so this drawing is going to help us. We know from our conversation before that triangles all have 180 degrees. So if we take our pentagon and we cut it up into three triangles, this has 180 degrees, so does this one, and so does this one, which means that the entire pentagon has to have 3 times 180, which is 540 degrees. So then how big is each angle in our pentagon, in our regular pentagon? It would be 540 divided by the total number of angles, which is 5. 540 divided by 5 is 108 degrees. And so in a regular pentagon, where all the angles are the same, all of those angles would be 108 degrees. And so once you know that information, once you calculate that, you can use your protractor. We talked about that in the previous video. You can use your protractor to actually draw a regular pentagon. So what would that look like? Step one, first thing you're going to do is draw a straight line and mark a vertex, right? Mark your like a starting point. Then you will grab your protractor and you will place the center of it, of the hole, right on that vertex. You will mark off your 108 degrees right there. So you're going to find that 108-degree angle. And then you will mark off two sides of equal length, right? So often protractor will also have measurement on it as well, right? So you'll make sure that you mark off a point there and a point there that are equal distant from that vertex. Then you're going to take your protractor and you're going to just rotate it over to the side you just drew and repeat that process at 108 degrees. And you just keep going with that until you get all the way back around. And so that's how you can draw any regular polygon. Again, going back to what we started with, however many sides the figure is, you can figure out the angle measure by calculating the total number of degrees and then dividing by the total number of sides in the figure. From there, You can draw really anything. And again, if you are following along on the slides, there is sort of a problem-solving application that I would challenge you to investigate. And it's what's the measure of each vertex angle in a regular 50-sided polygon. We just did a pentagon that has 5 sides, but see if you could do that. And there are a couple other follow-up questions along with that in that slide deck.